Harmonic motion refers to the motion and oscillating mass experiences when the restoring force is proportional to the displacement but in opposite directions. The simple harmonic motion is the motion of a mass on a spring when it's subject to the linear elastic restoring force. It's periodic and can be represented by a sine wave with constant frequency and amplitude. The motion equation for a simple harmonic motion contains a complete description of the motion.
For this experiment, we use around 35 coin, tape, thread, pushpin, and a piece of smooth wood. For the support, we put 2 tables separated by the wood length. Firstly, we did 7 columns of 5 coins each. Then, we wrap it with tape and thread. Secondly, we measured 2 things, the length of the 7th thread and the length of the wood. We divided that length in 7 equal parts and marked each one with a pushpin.
To finish our project, we tied the mass with our strands and attached each one in every pushpin. We put the stick between 2 tables and set a line perpendicular to the floor that served us as the origin. Then we drew an hypotenuse to find the 20 degrees angle between the origin and the new line. With a piece of cardboard, we moved the 7 pendulums at the same time with an inclination of 20 degrees. The movement of the pendulum lasts for 9.5 minutes. The video is fast forward on purpose.
Well, so as we saw, the pendulum waves were described by a movement called simple harmonic motion, in which the force is restored. Nonetheless, it is diminished by a constant that we know as B. We are going to try to find this B in what was our experiment, and to do so, the first thing we have to do is determine what is going to be X, or what's the position of the pendulums in a certain time. Since we cannot know with certainty where is the pendulum in each moment, we have to assume a time that is almost when the pendulums are almost stopped, and that is a value really close to 0, meaning that we have to assume that X is equal to A divided by 10,000. That occurs in the time 9.5 minutes, which is more or less what it took our pendulums to stop. Substituting these values on this equation, we get that B is 42.658 grams per minute. And we just had to take this part of the equation, since in the last moment of the movement, the cosine is really close to 1, so we can assume that this is 1. Taking this value, we can now know, graph the different pendulums and how they were, how was their movement. To do so, we have to take this term, W prime, and expand it. And this is what we get. But from here, we can take the K as mg divided by L being the length of each string of the pendulums. And when we substitute that in this equation and this equation, we get this. And why don't we put plus the angle? Because we took our first moment as in an angle equal to 0, so this term is not needed anymore. With this equation, we got all the values. We have A, which we get from knowing the length of the string. This is A that we're looking for, and we know here we have an angle of 20 degrees as we measure, so we just have to take A out of the equation of the tangent, and we get that A is equal to L times tangent of 20 degrees. Knowing all these values, we can now plug it in a graph in a program in the computer, and as you'll now see, we will get graphs that are describing this type of movement. Starting from here, they are describing this type of movement. As you can see, the graphs are being diminished by this term right here, and we will see that since all the pendulums have the same value for B, even though the amplitudes of the graphs will be different, let's call it the cliff or the downfall of the graphs are going to be really similar. This is the graph of the pendulum with the longest length. As you can see, the waves that this graph described are constantly going down. This is given by the constant that we just described. This pattern is also seen in the other pendulums, as you are going to see now. This is the pendulum that's right next to the one we just saw, and as you can see, they are describing more or less the same graph. And as we go down in length, we also go down in amplitude. Nonetheless, the graphs are keeping the same cliff down. This is the second to last pendulum that we graphed, and even though the amplitude is a lot less than the first one, they are describing the same damping force.
To conclude, even we change the longitude of every pendulum, we could check that the constant expressed by the letter B was equal for every one of the pendulums. As we could observe in the equations, the constant found was current to the results we were expecting. These results showed us that the constant is equal to any pendulum without caring about the longitude of the rope, only if the angle in which the movement starts with the rest point is between -20 and 20 degrees. Finally, the graphs given a few minutes back showed that when we introduced the constant, it proportionally matched to the experiments made. This permitted us to conclude when and how the movement of the simple harmonic motion met its end. Recommendations. We recommend using a better method to tie up the mass that will oscillate in every pendulum. In the same order, we would also like to remind to every listener that it is of utmost importance that for the sake of every experiment, each of the masses subjected to the pendulum must be equal.